All right, guys. So in this one, we are just going through, continuing going through the 2018 exam, the FRQ portion of the exam. And we left off on question 2, so let's get into it. All right, so we got 2NO plus O2 yields 2NO2. A student investigates reactions with nitrogen oxides. Okay, so NO and NO2. One of the reactions in the evaluation requires equal moles of NO and NO2. When the student produces, which the student produces by using the reaction represented above. All right, so the particle level representation of the equal molar mixture of NO and NO2 in the flask at the completion of the reaction between NO and O2 is shown below in the box at the right. So this is after the reaction. In the box on the left, draw the particular level representation of the reactant mixture that would yield this product mixture. In your drawing, represent oxygen atoms and nitrogen atoms as indicated below. So just a circle, oxygen atoms. A shaded circle is a nitrogen atom. They're both basically the same size. All right, so notice like right here, this would represent an NO2, and this represents an NO. Okay, so notice we have 1, 2, 3, 4 NOs, and we have 1, 2, 3, 4 NO2s, right? That's what equal molar means, equimolar here. Okay, so understand, and also look, there's no oxygen here. So over here, our O2 has to be our limiting reactant. And we have to understand that for every NO that reacts that we lose, we're going to get an NO2. It's a 2-to-2 or 1-to-1 ratio there. So we produced 2 NO2s. Okay, we produced 4 NO2s. And that means that we would need 4 NOs to react. Well, if we needed 4 NOs to react, but we needed 4 left over, we needed 4 of these left over, that means a total of 8 of these would react. And if 4 of these react, 4 times 1 over 2, that means you need 2 oxygen molecules. So to cause 4 of these to react, you need 2 oxygen molecules. So our reactant mixture should have 2 O2 molecules and 8 NO molecules, right? So let's go there. So we would remember O2, you'd have to draw 2 O's together, right? Not just a single O, right? So 2 O's together. But we would need 8 of the NOs and only 2 of the O2s, okay? All right. So we move to the next one. All right, so student reads in the reference text that NO and NO2 will react and react as represented by the equation below. This is the thermodynamic data for this reaction here. Notice that delta G is positive. What does that mean? It means at this temperature, the reaction is not thermodynamically favored. Okay? Notice delta H is negative. That means it's an exothermic reaction. Heat is a product. And delta S is negative. So it's an increase in entropy, a decrease in entropy. So, and that makes sense. We got 2 gas particles going to 1 gas particle, so that would be a decrease in randomness. So delta S should be negative. All right. Now the question, calculate the value of the equilibrium constant K. All right. Well, there's an equation for that on our formula sheet. If we have delta G, we can calculate K. All right. Here is the equation, and this is the equilibrium constant K. So we have to isolate K. K equals E raised to the delta G over negative RT. But when we do this, the R value that we use on our formula sheet is the 8.31 4 value. Again, that R value is on your formula sheet, and that's in joules. So the delta G that we use can't be kilojoules. The delta G that we use has to be joules. So it was 0.87 kilojoules, multiply that by 1,000. I think did I do that right? So that should be 8,700, not 87,000. So I messed that up. Hold on. Okay, so obviously I messed that up. That's not, point 0.7 wouldn't be the right answer. Again, it wasn't 87 kilojoules. It was 0.87 kilojoules. So 1, 2, 3. So it should be 8,700 should be what I have up here, not 87,000. No, it should just be 8. Would it be 1, 2, 3? It should just be 870. All right, sorry. So if it's 870, if it's 870, the K value is not going to be 0.7. It's going to be something different. Let me calculate it real quick. Hold. Okay, so scratch that. The correct answer is 0.7, but not when you use 87,000 here. So I guess I just miswrote it on the key. But if you, this should not be 87,000. This should be 870 on top. But when you put 870 on top here, you do get 0.7 for the equilibrium constant. And it should make sense because remember, if delta G is positive, the reaction is not thermodynamically favored, which means KEQ is less than 1. So we should expecting something less than 1. But that's not that big of a number for the delta G value. So it's not thermodynamically favored, but it's not crazy unfavored. So the equilibrium constant isn't going to be that small. Okay. All right. Yeah, I don't know why my key was wrong there. Anyway, so we calculate the value of the equilibrium constant. If both the partial pressure of NO and the partial pressure of NO2 in the vessel are initially 1 atmosphere. So before the reaction, if this is 1 atmosphere, that 1 atmosphere, the total pressure in the system is 2 atmospheres. Will the partial pressure of N2O3 at equilibrium be equal to 1 atmosphere? Well, the only way the partial pressure of this could be equal to 1 atmosphere is if the reaction goes to completion. Because, 1 atmosphere of this can produce 1 atmosphere of that. It's a 1-to-1 ratio. 1 atmosphere of this can produce 1 atmosphere of that. It's a 1-to-1 ratio. So the only way that the overall, or the partial pressure of this is N2O3 is 1, and you started with these two at partial pressures of 1, the only way that could be a partial pressure of 1 at equilibrium is if the reaction doesn't reach equilibrium, is if it goes to completion. So the answer is no. The only way the pressure could reach 1 atmosphere is if the reaction goes to completion. The equilibrium constant is less than 1, so the reverse reaction is more favored than the forward reaction. The pressure will be closer to 2 atmospheres than 1 atmosphere. So yeah, the pressure is going to decrease as this reaction approaches equilibrium because you don't have any of that. But you'll still have more of these gases than you do that gas because the reverse reaction is more favored than the forward reaction. Okay. All right. Let's see, part D. Student hypothesis that increasing the temperature will increase the amount of N2O3 in the equilibrium. Indicate whether you agree or disagree with the hypothesis and justify. Well, you have to disagree because an increase in temperature would not cause this reaction to shift to the right. It would cause this reaction to shift to the left. And the reason you know that is because it's an exothermic reaction. That's what this delta H is telling me. So heat is a product. So adding heat would cause it to shift this way, and you would end up losing more of the N2O3, not gaining more of it. So disagree. Increasing the temperature of an exothermic reaction would would favor the reactants, not the product. Let's see. The reaction is exothermic. Increase in temperature would favor the reactants. There you go. That works. Okay. All right, part D. Reacts with water to produce nitrous acid, a compound involved in the production of acid rain. The reaction is represented below here. Okay. So this reacting with water to produce nitric acid. The skeletal structure of the HNO2 molecule is shown in the box below. Complete the Lewis electron dot structure of the HNO2 molecule in the box, including any lone pairs. So notice it didn't say anything about formal charge. So this could have a couple answers that would be acceptable, but I think my key, I have the one that's the correct formal charge, okay? So first, know how many dots should be in the structure. So 1 for the hydrogen, 6 for each oxygen. So we got 1, so we got 6 plus 6, that's 12, plus 1 is 13, and then 5 for the nitrogen. So we got 18 dots. So our final structure needs 18 dots. Oxygen's a must-have 8, nitrogen's a must-have 8, oxygen's a must-have 8, and hydrogen's a must-have 2. So you know there's only just one bond in between H and O, because hydrogen can't support any more. So make one bond for each thing, right? And then you could start adding lone pairs. I would put 2 lone pairs on the oxygen, 2 lone pairs on the nitrogen, and then 3 lone pairs on this oxygen, and see how many dots that is. That would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's too many. I can only use 18 dots. So what we can do is take a lone pair away from this oxygen, that would be 18, and then take one of the lone pairs on the nitrogen and make it a double bond between that oxygen, and that would maintain the 18 and give everyone a satisfied octet. So this would be what you would draw, okay? And this would be the better structure in terms of formal charge. And then this is more of like what the shape would it be, like if it asked for, you know, this bond angle is not 180, that would be around 120, but this bond angle here would be around 105, right? The bent bond angle, or 109, you could say. So all that kind of thing, okay? But that would be the correct structure, all right? And then based on the diagram above, identify the hybridization of the nitrogen atom in this. So the nitrogen atom, so this is where if you had a different structure, whatever your structure had, make sure your answer to D2 agrees with whatever you have. So the nitrogen has 3 domains, 2 bonding domains and 1 unshared pair, but that means 3 total domains, and 3 total domains hybridization is sp2. Okay, so this oxygen would be sp3, the nitrogen here is sp2, and this oxygen would be sp2 as well, because it also has 3 domains around it. So this oxygen would be sp3, but this nitrogen and this oxygen, they both would be sp2, just in case they ask about the other one. All right. All right, so here we got a titration curve. It's being titrated by potassium hydroxide, a strong base. We already know that HNO2 is a weak acid, but we know it's a weak acid because look at the equivalence point. It's above 7. The pH is above 7, so we know the acid being titrated is a weak acid. So then we know that NO2 minus is a weak base. So these are all kind of things that we can be kind of knowing just by looking at this chart. And then part E1 shows, use the titration curve to determine the initial concentration of the HNO2. So this will do MAVA equals MBVB. To get the volume of the base, go to the equivalence point, so the point of inflection. So 20 milliliters of the base. So 20 milliliters is our volume of the base. This is our molarity of the base. What did it say? The student titrates 100 milliliter sample of the solution. So our volume of our acid, our VA, is 100 milliliters. Okay, so let's see how we did. Yep, so we had 100, so this is what we're solving for. VA is 100, molarity of B was 0.1 of the base, and the volume of the base was 20 milliliters. That was the equivalence point on the titration curve. So the molarity of the acid comes out to be 0.02 moles per liter. Okay. Okay, so that's the molarity of our acid, all right, from the titration data. And then it says estimate the pKa. So just remember, the half equivalence point is where pH equals pKa. So if our equivalence point's at 20, half of that is 10. So we would just go up to the chart, and we're just a little bit above 3. We're in between 3 and 4. I wouldn't say we're at 3.5 yet. This would be an estimate, so it might be different. I would expect 3.2 or 3.3 to be probably the most popular answers. Probably 3.4 would be allowed as well. But yeah, my estimate was 3.3. Okay. Now, if we wanted the Ka, we could do 10 raised to the negative 3.3. That would give us our Ka, but they just asked for the pKa. Okay. So during the titration, after the volume of 15 milliliters of 0.1, so that puts us here in the titration. What do we have more of, the HNO2 or the NO2 minus? So remember, in a titration, the way we would represent it is before the start, all we have is NO2. And as we go from the start of the titration to the equivalence point, we're slowly losing this and steadily gaining this. Okay, and then by the time we get to the equivalence point, we don't have any more of this, and all we have is that. So the half equivalence point is where they're equal. Anything before the half equivalence point, you would have more acid than the conjugate base, but anything after the half equivalence point, you would have more of the NO2 minus. Okay, so the answer would be this, the NO2 minus is more concentrated. So NO2 is in higher concentration. At the half equivalence point, the amount of this equals the amount of that. Beyond the half equivalence point, more HNO2 has been neutralized, which produces more of the NO2 minus. Okay. So if they had asked the same question, but they had asked about the 5 milliliter mark, we would have more of the nitrous acid in solution and less of the nitrite. All right. Okay. So that was question 2. All right. Hold on. Sorry, just real quick, just another explanation for question 2F. You could use the Henderson-Hasselbalch because if you recognize you're in the buffer region. The pH, so at 15 milliliters of, let's go back. At 15 milliliters of this added, our pH is higher than the pKa. And so the only way the pH can be above the pKa is if you have a bigger number here than here. So that would be that ratio has to be greater than 1. That's going to give you a pH greater than the pKa, which is true when you're beyond the half equivalence point in the titration. Okay? All right. All right, so we'll stop this video here and we'll move on to question 3 in the next part, in part 3. All right?